Hello, everybody. Let's start the lecture. So today I would like to present you motivation of the course, like syllabus, the questions that we want to investigate. And the motivation is the following. I would like to present mathematical models for diffusions in a media with semi-permeable membranes. Such models appear naturally, for example, in molecular biology, when you have some diffusion, say, of antibiotic in a cell, and there is a membrane, and when a particle hits membrane, sometimes it's reflect, but sometimes, maybe with smaller probability, it can penetrate. And here you see a diffusion again until it hits this membrane again. Or these models, such models may appear, for example, in telecommunication. And assume that we have a server, that processes some information. And this is time, for example, in seconds. And here is the number of, say, megabits of information that wait processing. And if you see this scale, seconds, megabits, you'll see some continuous process, which is non-negative because Q is non-negative. And okay, in some sense, with some reflection, sometimes there are no bits in the line and the server is idle. And well, you reflect, and here you see behavior like a diffusion process. Before we start to investigate diffusions in a media with semi-permeable membranes, let us discuss what is the most famous example of a diffusion. And the answer is probably a Brownian motion. By the way, who was botanist? Have you any idea? Like mathematicians or physicists? Okay.
Well,
Yeah. Who?
a biologist?
Yes. Botanist. Yes. And he studied pollen, and he took a microscope. And when he took a microscope and looked at the pollen in a water, he discovered that pollen moves randomly. And now this motion is called Brownian motion. However, Brown didn't know a reason for this. And a natural guess was that pollen is alive, like a small animal, very small animal who flies. Well, actually, this is not true, as we know. And we know that pollen moved because of collision with atoms of water. However, this effect was explained probably 70 years after discovery of Brown. And we will start with random walks. So macroscopic description of Brownian motion. And the simplest model is the following. Each step, very small interval of time, you have the particle, this is time, this is position. A particle moves randomly, so it makes a jump. And we assume that jumps are independent, identically distributed random variables. I will continue. I will define this motion by linearity, and a position of a particle at a moment of n is a sum. Initial position plus sum of jumps. Psi n is a jump at the moment n. And usually the interval between jumps is very small, and jumps are also small. So this picture we will see if we observe motion of particle in milliseconds, for example, and 1/100th of millimeter. But if you speed up the time, and if you consider not in 1/100th of millimeters, but in centimeters or in meters, then you will see a continuous process, which is a Brownian motion. Okay, if you consider proper scaling of time and space, we will discuss this later. And what is a model for diffusion of a Brownian motion in a media with a semi-permeable membrane? Well, in this course, we will consider one-dimensional case. So assume that a particle lives not in a three-dimensional space, but on a line. Okay, assume that there is a certain membrane. For example, this membrane is located at 0. And if particle travels here, then its jumps are independent, identically distributed random variables. But when particle hits membrane, its behavior is different. For example, membranes can push up with certain probability, say 0.9, and pushes down with probability, so just step 1 unit, and with probability 1.0. So assume that it's very complicated to pass through the membrane. But if you pass through the membrane, and if you're here, then you have again regular random walk. You add independent, identically distributed random variables, and at the next hitting, again, you have some probabilities, for example, P and Q, to make a step upward or backward. And when you are here, again, you have ID increments. By the way, if we consider my model from telecommunication, assume that we receive and we process bits of information every millisecond or every tick, so every very small instant of jump, then the number of bits is a random walk. It's a random walk. Sometimes there are more bits, sometimes less, so you process more than arrive, and so on and so forth. But sometimes you can process more than you have. So theoretically, your server assumes that you receive no bits of information, and your processor is fast and can process everything. And theoretically, if it could, then the next jump would be here. But if there are no bits of information, then the server stops working. So actually, you don't jump here, but you jump here at 0. And this means that 0 is somehow a reflected membrane, as a reflected screen. You cannot pass through it. We will discuss different types of reflection, and natural possibilities to reflect. For example, if you have a server and if there are no bits of information, it can wait a certain amount of time to accumulate new bits. But then if a new bits of information arrive, then you'll have a big jump from zero. So unusual jump, not like here. And if you are here, so if you have some queue of bits, then you can process similarly to these rules. You have more and or less bits of information until there are no bits of information in a queue. And then you make some scaling and consider not milliseconds, but seconds or minutes, and not bits, but megabits. And in a limit, after this scaling, you will see not jump process with jumps, but a continuous process that looks like a Brownian motion with certain reflection at zero. Okay, so the plan of my course is the following. At first, we will investigate random walks. That are sums of independent, identically distributed random variables. We will find some probabilities, expectations, maybe discuss transients or recurrence. Calculate moment generating functions and so on and so forth. Well, we will start with the simplest examples. Then we will discuss Markov chains. That are generalization of random walks. Actually, this model that I draw, so regular behavior here, and certain irregularity at zero is a Markov chain. So we will discuss some general questions for Markov chains with finite or countable number of states. Then we will discuss convergence in distribution. Well, I've told you that the limit of these perturbed random walks should be a Brownian motion with reflection or with some semi-permeable membrane. But the question is, okay, Brownian motion is a limit of a random walk, of scalings of random walks, but what type of limit? In probability, in almost sure, limit in distribution. So this will be a convergence in distribution, and we will study some general theorems from this topic, and then we will discuss a Brownian motion. Brownian motion, its properties, and we will explain how we can get a Brownian motion as a limit of random walks. And then we are going to investigate limits of perturbed random walks, with semi-permeable screens or with reflecting screens. And the next topic will be random walks with reflection. Uh, and as application of this theory, we'll discuss Brownian motion with reflection. Reflection and different approaches for constructing this process. And the next topic will be random walks with semi-permeable membranes. And the limit of this will be Brownian motion. Oh, excuse me, not Brownian motion, will be a skew Brownian motion, a Walsh process, and so on, that can be considered as diffusion in a media with semi-permeable membrane. Okay, informally, this skew Brownian motion is the following process. It behaves like a Brownian motion if it is outside of zero. So if you're outside of zero, then this process behaves in some sense. So this is not rigorous as a Brownian motion. But when you hit zero, you start a new excursion above or below with certain probabilities. For usual classical Brownian motion, this probability is 1/2 and 1/2. And for this skew Brownian motion, probability to go up is p, and probability to go down is q, which is 1 minus p. And in particular, if p is 1, then you'll get reflected Brownian motion. All excursions will be positive. Okay. However, you have to be very careful when you talk about excursions of Brownian motion and this probability to go up or to go down. You can define certain probabilities for Markov chains in discrete time, but everything is very complicated in continuous setting. If you studied Brownian motion a little bit, you may know that if a Brownian motion hits zero, then in arbitrary neighborhood of this point, there are infinite number of moments when the Brownian motion hits zero. So this means that the picture is approximately like this. You have very small excursion here between two zeros, and here, and here, and here. And for Brownian motion, there is no next excursion. So my statement that we select direction of reflection P and Q is not very rigorous, but in some sense, however, it makes some sense. Okay. Well, when I said about certain limits, we need to give a rigorous definition. What is a Brownian motion, or what is a reflection Brownian motion? And it would be nice if you know a little bit a theory of Markov processes. Of Markov processes. But if you don't know, so don't worry, I will give all definitions, and the course is self-contained. Well, maybe you know a lot of things from random walk theory or theory of weak convergence. However, I don't know the level of students. So if everything is obvious, please tell me. And if you have any questions, don't hesitate to stop me and to ask. Okay. Uh, Now we start the first topic, and the topic is simple random walks. And we start with definitions. We assume that psi n be independent, identically distributed random variables, and a sequence, random sequence Sn defined by x plus xi1 plus xi2 plus and so on plus xin is called a random walk. Is called a random walk, and xi1, xi2, xin are jumps of this walk. Well, we will also define a0 as x, and sometimes I will write here subindex xi to emphasize that the distribution of jump is xi. You may see that position of random walk at the moment n+1 is equal to position of the random walk at moment n plus xi n plus 1. So increment or jump of random walk is equal to xi with the corresponding index. This x is non-random number. Sometimes people consider random walks that start from random variable, and if x is a random variable, we will always assume that this initial starting point is independent of this random walk. If x is 0, that is Sn is just xi1 plus xin, then we will call this a standard random walk. And random walk. Okay, and today we will consider a particular case of a random walk. Where xin are symmetric random variables that take values 1 or -1 with probability p and q respectively, where q is 1 minus p. And in this case, I will say that xi is a simple random walk. Okay. So this is time. This is position. Assume that we start from x. X will be integer number, and the random walks make jumps plus or minus ones. Well, this graph is not nice. It's easier, and it's for visual to understand the graph better. It is convenient to continue our random walk by linearity. Okay, and I will always assume that S psi defined for every t by linearity. Okay, and the first question that I wish to discuss is to calculate transition probabilities that S at the moment n is equal to y, given S of 0 is x. So x, y are integer numbers. Okay, so this instant is n, this position is y, and the first question is this. Well, the first lecture will be simple, and this is very classical stuff. The second lecture will be more complicated, and then we will study more advanced topics. Okay, how to calculate this probability? Please recall me if you know. Кирилл, Геннадий, Вадим. Are
We need first to compare y and x, and like in n steps we can only go up n steps or go down n steps. So we need to check if this distance between x and y is less than or equal than n. And then we need to count all possible trajectories. So in each
yes.
step we have two options, so 2 to the n. And if we are at y, then we need to make the exact number of jumps up and jumps down.
Oh, yes, you're right. Thank you. So it's easier to start from another problem and to calculate, to take certain path. For example, xi at the moment 1 is equal to I1, xi at the moment 2 is I2, and so on. Xi at the moment n is In, and let's calculate this probability if you start from certain point I0. So forget about x, about y, for example, and assume that this point is I0, I1, I2, I3, and we will assume that ik plus 1 minus ik is either 1 or negative 1. Otherwise, this probability is 0. Okay, and this probability is equal to the following probability. That, okay, what is the value of the first jump? The value of the first jump is I1 minus I0. And so xi1 is equal to I1 minus I0. And the second jump is equal to I2 minus I1, and so on. And xin is equal to in minus 1. And these random variables are independent, and they have the same distribution. So probability of intersection is equal to product of probabilities. So you can write probability of this times probability of this, and so on, times probability of this. And each value is either P or Q. So the answer is P raised to the power number of jumps up times q raised to the power number of jumps down. And that's all. And if we want to calculate this probability, then you need to do the following. This probability is equal to sum of probabilities that you start from x, and here you should write all possible paths, that s of 1 is y1, s of 2 is y2, and s at the moment n is in, okay, where in is y, and these paths should be admissible, so each step is either 1 or -1. And we know that, okay, if you start from x and if you finish at y, you may solve the problem how many steps are up and how many steps are down. Okay, so let me write it like this. Sum over all possible these ik, all possible paths, I0 is x. I forgot to write here that we start from x and we finish at y, and p raised to the number of steps up times q times number of steps down. And let's calculate. Well, let a be a number of steps up. Then number of steps down is n minus a. Indeed, not all steps, n steps minus number of steps a. And when you go up, you add 1. If you go down, you subtract 1. So number of steps up minus number of steps down is equal to y minus x. So you start from x. So this is vertical motion during n steps. So a steps up and n minus f steps down, and this equals y minus x. And if you solve this equation, you will see, so a plus a2a minus n is y minus x, so 2a is n plus y minus x, so a is n plus y minus x over 2. And we see that all of these probabilities are the same. So the answer is equal to number of admissible excursions from x to y, number of excursions, number of paths, okay, number of paths from x to y, times p to the power a, where a is this number, times q, n minus a. And the next question, what is the number of path from X to Y. Number of admissible path. So the path is admissible. Okay. If you make A steps up and n minus A steps down, then you will definitely reach Y at the moment n. So if A is a number between 0 and n, is an integer number between 0 and n, then the number of path is n choose A, that is n factorial over A factorial times n minus A factorial. Indeed, you have n steps and you select A places to go up and n minus A steps to go down. So the answer is this. So the final answer is the following. N choose n plus n choose A, but we know that A is n plus y minus x over 2 times p to the number of steps up n plus y minus x over 2 times q n minus this number. So n plus x minus y over 2. If this number a, which is n plus y minus x, is integer number between 0 and n. If y minus x less than or equal to n, and this number is even number, n plus y minus x is even number. Otherwise, the corresponding probability is equal to 0. Well, for example, you cannot reach the point 2 starting from 1 in 2 steps. You may reach only 1, 3, or -1. And you may not reach 2 because this is odd number in this case. And for example, you cannot reach the point 10 because the difference 10 minus 1 is greater than number of steps greater than 2. Okay. And now let's continue. And the next question is the following. We consider simple random walk. We start from integer point x and the question is how to find the distribution of the first instant when you hit 0. Indeed, when we discussed the process with membrane, it was important to know, okay, now we here before this moment tau, we have some regular behavior, and it's interesting. What is the distribution of tau? So the second question is this. Let tau be the first instant such that S psi of n is 0. And the problem is to find distribution of tau. Find distribution of tau. This means that you have to find probabilities that tau is n. And we will start with the so-called André's reflection principle. And the general question is related to the previous problem. However, it's a little bit different. So we start from x, we end at y. This is moment n. And the question is how to find the probability that you visit a point y at the moment n, but you never hit 0 before instant n. So this path is prohibited. So the mathematical problem. So let x and y be natural numbers. Find probability that the random walk, the random walk is positive. So the random walk does not hit 0. S of 2 is positive. S n minus 1 is positive, and Sn is y, given S0 is x. Okay, and let's try to find the answer. And the answer is this. So we will call this path admissible. We will consider all admissible paths from x to y. So paths that have jumps +1 or -1 and don't visit 0 before moment n that ends at y and starts from x. So number of all admissible paths from x to y. And we know that the probability of each path is p to the number of steps up times q raised to the power number of steps down. Well, and now we consider only the case where this number is not 0, so that you may reach y in n steps. So y minus x does not exceed n plus y minus x is even number, and so on and so forth. So the only question we have to consider is how to find the number of paths from x to y such that the path is that this path does not reach 0. Okay, once again, so we start from x, we finish it at y. So this instant is n, and the number of all admissible paths is equal to number of all paths from x to y. And it's easier to calculate the number of paths that actually hit zero, than the number of path that does not. So minus the number of bad path. The number of path from x to y that visit zero. Visit zero before instant n. And make a picture of this bad path. So this is good path, and now a picture of bad path. So it visits zero, maybe few times, and then arrive to y. And now let's make the following trick. This is the first instant of hitting, and then we take this part and reflect it, flip it, and consider the following. Okay, the following. If this point is y, then this point is negative y. And we see that it's easy to see that the number of all paths from x to y that hit zero before instant n is equal to number of all paths from x to y that also hit zero. So number of bad path from x to y is equal to from x to y is equal to the number of all paths from x to negative y, and observe that if the path start from positive number and ends at negative number, then this path for sure hits zero. So here I wrote that path from x to y that visit zero, but when I consider path from x to negative one, I may skip this information that the path from x to negative y that hit zero. If this number is positive, y is negative, then and if you come from here to there, then you will hit zero. So, and we know this number. N steps, you start here, you end here. We know the number. This number is equal to n. Choose the number of steps up, and the numbers of step up is this, n plus final point minus y minus initial point x over 2. So n, choose n minus y minus x divided by 2. And now we can write the answer. This probability is equal to total number of paths from x to y, and choose n plus y minus x over 2 minus number of bad paths, and choose n minus y minus x over 2 times p to the number of steps up times q raised to the power number of steps down. Okay, and let us discuss few generalizations of this of of this problem. And the next question is this. Assume that x and y are natural numbers. How to find the probability that the random walk starts at x, ends at y, and is non-negative? Okay, so theoretically you may hit 0, but you can't cross 0, so these paths are prohibited. Okay, please help me. Have you any ideas?
So it's the same, but we need to reflect y uh, relative to -1.
Yes, you're absolutely right. And we can write formally, okay, a new axis and say that, oh, the number of paths that are non-negative is equal to the number of paths that never hits -1. Or you may say, okay, this is a new 0. Then this point is x plus 1, and this point is y plus 1. And this probability is equal to probability that S1 is positive, S2 is positive, and so on. Sn minus 1 is positive, and Sn is y plus 1, and S of 0 is x plus 1, and then you know the formula. Actually, I don't insist that you remember all the formulas with these binomial coefficients. It's more important to understand the way of proof, how to calculate the corresponding probability. Okay, great. So this is the answer, and you have a formula for this. And another question is this. Okay, let's consider the following picture. We actually used here the fact that x and y were natural numbers. And now let's consider the problem when y is equal to 0. Oops. And let's try to calculate the probability that the random walk starts at x and n is the first instant when you hit 0. So please, any ideas? Or let's calculate.
Well, it's this n minus 1 should be 1, then n not touch 0.
Yes, if this instant is n minus 1, then this is 1. Okay. Well, and you're right. So the number of admissible paths from x to 0 is equal to the number of paths from this point to this point that never visited 0. Number of paths from point 0x, so 0x, to n minus 1, 1, that don't visit the axis, OX. And you know how to calculate this, and you know the formula. And next question, you start from x, and let me recall you that I denoted by tau the first instant, such that s of n is 0. And my question is how to calculate, how can we calculate probability that tau is n, that the random walk visits 0 at the first time at the instant n. And hit, it is related somehow to previous examples.
So it's exactly the previous probability
Yes,
from our drawing.
yes. So this is exactly this probability. So we found distribution of the first instant of hitting 0. However, moreover, we are able to calculate more interesting probabilities. Okay, and new question is this. Well, assume that x is 0 and y is 0. So we start from 0. Random walk is positive. At the moment n, this is the first return to 0. So how to solve this problem?
The number of paths will be the number of paths from point 1 to point 1, but in n minus 2 steps.
Yes. So we know that the first step must be +1, the last step must be -1, and we start from this point, we end at this point, and we always positive, and there are n minus 2 steps here. So number of paths is equal to number of paths from 1, 1 to n minus 1, 1 that do not visit 0 or visit excess of x. And we also know the answer, and the homework will be calculate certain probabilities for random walk. And the last question that I want to discuss is the distribution of maximum of a random walk. So the problem is to find distribution of maximum of sk, k between 0 and n. And without loss of generality, we may assume that the random walk starts from 0. Start from 0. So this instant is n. This is maximum of sk, k between 0 and n. And the question is how to find the distribution of the maximal value. Okay, and the question is, are there any ideas? So let's investigate this. Gennady or Vadim?
So I think we can also reflect relative to maximum.
Yes, and then yes, okay. At first, we have to write a probability. So we need to find, say, probability that maximum of sk is equal to certain number in order to find the distribution. Or a probability that maximum, for example, exceeds certain number. Okay, so for example, maximum is greater than or equal to certain number x. Well, this is not a distribution function, but it's close to the distribution function. Well, and now let's make a reflection. So if maximum is greater than or equal to the point of x, then
We can introduce some random time tau.
Yes, we may yes, we may reflect these paths we may reflect this path with respect to this line? Well, I wish to say that if you reflect with respect to maximum, then this path is always above this line, but this is not the case. But
So we reflect not with respect to maximum, but with respect to x, right?
yes, maximum is a random variable.
Mhm.
So let's calculate the number of admissible path. Yes, let's calculate. Let us calculate this. So we will not calculate this probability. So let's just calculate the number of path, and in this case, let us assume that Q is 1/2. So every path has the same probability, 1 divided by 2 to the power n. So let's restrict ourselves to this problem. And number of admissible path is equal to number of path that hit x and ends above x, plus number of path that hit x is below x, and the number of path. Oops. So let me use a different color. For example, hits s x and ends at x, or maybe or ends at x like this, is number of path such that s of n strictly greater than x plus number of admissible path it's easier probably to write probabilities in this case. Okay. So maximum is greater than x is equal to probability that maximum of xk is greater than or equal to x, and s at the endpoint is strictly greater than x, plus probability that maximum of sk is greater than or equal to x, and Sn is strictly less than x, plus probability that maximum of Sk is greater than or equal to x, and Sn is x. Well, and here we will assume that P is Q is 1/2. So every concrete admissible path has probability 1/2 to the power n. And now observe that this probability is equal to this probability. Indeed, we use reflection principle, and if we reflect some path at this moment when you hit x at the first time, if original path was below x, then reflected path is above x, and vice versa. If the first path was above x at the end, then reflected path is strictly below x at the end. So this probability is equal to this probability, so we may write just two probabilities that maximum of sk is greater than or equal to x, and Sn is greater than x, plus this one, probability that maximum of sk is greater than or equal to x, and Sn is equal to x. And now please help me. We can simplify this expression a little bit. So any ideas?
If Sn equals x, then we automatically get that maximum is greater
Yes.
than or
If
equal.
Sn greater than x, then this is true. Maximum is greater than or equal to x. Okay, we may. And what about this probability?
Oh yeah, the same. So if
Yes.
it's
If
bigger,
if Sn is greater than x, then maximum certainly is greater than or equal to x. So the answer is 2 probabilities that Sn is greater than x plus 1 probability that Sn is equal to x. Or we may write a probability that, so if we write this like Ps, okay, this is equal to 2 probabilities that Sn greater than or equal to x plus 1. Well, Sn is integer valued random walk plus probability that Sn is equal to x, or if we write this like Sn greater than or equal to x plus 1 plus Sn greater than or equal to x plus 1. So this expression is equal to Sn greater than or equal to x plus 1 plus probability that Sn greater than or equal to x. Okay, we have this probability, and now let's calculate probability that maximum is equal to x. So how to find this probability?
so we need to subtract x plus 1, so substitute x plus 1 and subtract the probability for x. So bigger than or equal than x plus 1, than x. Uh, uh, mm,
This is almost true, but
no, no, no.
this is not correct.
Yeah, bigger than or equal than x minus, and there x minus 1.
Here, please repeat.
Oh, yeah, sorry. Here x plus 1.
X plus 1. Yes. And if we substitute this, then we get probability that Sn greater than or equal to x plus 1 plus probability that Sn greater than or equal to x minus probability that Sn greater than or equal to x minus probability that Sn greater than or equal to x minus 1. No. No. Oh, excuse me, x plus 2, and here x plus 1. And now we have to make some cancellation. So this probability minus this probability and this probability minus this probability. So this minus this is equal to probability that Sn is x plus 1. And this minus this probability is equal to probability that Sn is x. Actually, only one of these two probabilities may be not zero. So at least one of these is zero because of because n minus x, is it even or odd number? So if you may reach x, then you cannot reach x plus 1. Okay, and for this, you know formulas, and hence we get the distribution of the maximum of a random walk. So that's all for today. Thank you for your attention, and see you next week. Oh, well, one question. Are there any questions or comments?
Do we have a recording?
I hope so. And yes.
It is recording.